Good morning. Welcome to the encryption session. First of all, apology for the people that are mispronouncing names. So this is an encryption session. The first talk is multi-authority function encryption with bounded collision from standard assumption by Rishab Goyal and Shaikumar Yadguri. And Shaikumar will give the talk.
Hi, good morning, everyone. I'm Sai Kumar Yadguri, and this is my joint work with my advisor, Rishab Goyal. First of all, let me recall the notion of functional encryption. So functional encryption is a generalization of public key encryption in which there is a trusted authority that generates the master public and master secret keys for the system. And we can encrypt functions using the master public key, and the trusted authority issues secret keys for inputs X using the master secret key, and the evaluator can use these to learn f of X and nothing else. Multi-authority functional encryption is a generalization of public key encryption where the main idea is that the key generation is split across independent, asynchronous, and mistrusting authorities. So more particularly, there are these N authorities who have their own master public and master secret keys that they generate on their own, independent of others. And encryption proceeds similarly to the plain FE case where we take all the master public keys to encrypt a function F. And now for key generation, the evaluator has to query each and every authority. So authority 1 issues secret keys for partial secret key for X input X1, authority 2 issues partial secret key for input X2, and so on. And the evaluator can combine all the partial secret keys to learn f of X. In order to avoid trivial mix and match attacks, we parameterize each user in the system with an additional unique string called global identifier, GID. GID could be anything unique to each user, like their passport number or their SSN. And even the partial secret key generation is now generated with respect to GID. And the idea of using GID is that two sets of partial secret keys that are generated for distinct GIDs cannot be combined to learn something non-trivial. For instance, if the GID is a passport, the hospital is going to look at your passport and give you a medical certificate. It's unlikely that the hospital is going to give you two medical certificates for the same passport. That way we use GIDs to avoid mix and match attacks. Security of multi-authority FE is similar to plain FE case, where the idea is that an adversary in possession of a ciphertext for function F and Q sets of partial secret keys for inputs X1 through XQ cannot learn anything more than f of X1 through f of XQ. And a weakening of this security is the bounded collision model, where the number of sets of partial secret keys that an adversary can receive is a priori bounded. So what do we know about MAFE? Well, we know how to construct MAFE for general circuits using sub-exponentially secure I/O as provided by Brakersky et al. In their ITCS 2017 work. And that's it. We don't know anything more about MAFE for general circuits. In particular, we don't know how to construct MAFE in the bounded collision model from simpler assumptions than what is required for obfuscation. And the lack of results in this domain can be explained by Brakersky et al.'s auxiliary result, in which they showed that an MAFE scheme generically implies an obfuscation scheme. And this implication is tighter even in the bounded collision model. So let's take a look at this implication to see why MAFE is this hard to construct. So in order to obfuscate a function f using MAFE, we encrypt the function using the master public keys from all authorities, and then generate two partial secret keys, one for bit 0 and one for bit 1 for the same GID from all authorities. So the obfuscation of a function is going to be the ciphertext along with these two N partial secret keys. However, in order for security of the obfuscation scheme to hold, we need an MAFE scheme in which we can corrupt two partial secret keys for the same GID from any authority. And this kind of collides with the classical motivation for using GID. I mean, GID was used to stop mix and match attacks. If each authority is going to give you two partial secret keys, then how are we protecting from mix and match attacks? The hospital is going to look at your passport and give you a medical certificate. If the hospital were behaving honestly, it's not going to give you two medical certificates for the same passport. So the security notion required for obfuscation is not exactly the bounded collision model definition we required for MAFE when we are working with GIDs. So starting from this observation, in our work, we ask the following question. Does an MAFE scheme for general circuits in which each authority is only going to give you one partial secret key per GID, and we call this authorities behaving semi-honestly, is this object enough for obfuscation, or can we construct this from simpler assumptions? And we show affirmative results for the latter, and we construct a 2 or 3 authority MAFE scheme from polynomially hard assumptions. And we also show in our work how to bootstrap this to any constant authority MAFE scheme from the same polynomially hard assumptions. And we also show how to construct an MAFE scheme with arbitrary number of authorities from sub-exponential public key encryption and random oracles. Due to time constraints, I'm only going to talk about the first result in this talk. And I'm going to show you how to construct a 2 or 3 authority MAFE, starting from a 1 GID MAFE, whereby 1 GID, we mean that the adversary is only going to corrupt one partial secret key from each authority, just one. And I'm going to show you how to amplify this security to handle arbitrarily large bounded collisions. And I want to emphasize that there are no random oracles required for the material covered in this talk. Everything is going to work in the standard model. Okay, so in order to construct a 1 GID MAFE, we look at the classical result from plain FE domain, which is by Sahai and Sayalioglu, in which they construct a 1 collision plain FE from public key encryption. So in their construction, during setup, for n bit inputs, they sample 2 n public and secret key pairs, 2n. And during key generation, they deterministically give out half the secret keys corresponding to input x. And to encrypt a function f, they garble the function and encrypt the wire labels under the corresponding public keys. And decryption follows naturally. Using the secret key, we can only decrypt half the wire labels and then evaluate the garbled circuit to learn f of x. So just by staring at this long enough, we can see that we can distribute the setup and the key generation among n independent authorities. So in order to construct a 1 GID MAFE, where the adversary only corrupts one partial secret key per authority, and we ignore GID in the syntax because of this, so each authority is going to generate 2 public and secret key pairs, just 2. And for key generation, it's going to give out one of the secret keys corresponding to the ith bit of x. And encryption and decryption remain the same. Using all the partial secret keys from all the authorities, we can still decrypt half the wire labels and learn f of x. So a 1 GID MAFE scheme can be naturally constructed from public key encryption thanks to Sahai and Sayalioglu's result. Now the main part is handling larger collision bound. So in order to do this, we look at one more classical result from the plain FE domain, which is by Gorbunov, Vaikuntanathan, and V. And in our work, we use similar collision bound amplification techniques. So let's review what's happening under the hood of GVW. In GVW, in order to construct a Q collision plain FE, starting from 1 collision plane FE, they sample n systems of 1 collision plane FE. And to encrypt a function f, they use a special threshold secret sharing scheme that decomposes f into n distinct shares. And we encrypt each of the shares under the corresponding 1 FE system. And on the other hand, for secret key generation, they sample a special subset S and only generate secret keys for the 1 FE systems in this subset, and for a special encoding of X, which I'll talk about in a second. So security follows naturally. We only, given information about S, we only decrypt the ciphertext in this subset and then use the threshold reconstruction to learn f of X. And so for security to work, we need the shares to be reusable multiple times. And because of that, we sample one more set delta, and the special encoding of X is nothing but X and delta together. So some intuition about these special sets S and delta. S kind of makes sure that the threshold of the scheme is not exceeded when we are sampling it multiple times. And delta makes sure that each of the share is sufficiently randomized so that we can reuse it multiple times. And more importantly, both of these sets have to be generated randomly each time. So now we have a 1 GID MAFE scheme, and we know what's happening under the hood of GVW. So let's generalize it. In order to construct a QGID MAFE scheme, starting from a 1 GID MAFE scheme, each authority is going to set up one GID MAFE schemes, n of them. And for encryption, we do the same thing. We secret share F and encrypt the shares under the corresponding 1GID MAF scheme. So nothing special is happening here. On the other hand, for key generation, previously we were generating a special subset S and only generating secret keys for there. But in MAFE, we face an issue. And the issue is because of the independent nature of each authorities. Because each authority acts independently and asynchronously, they only look at a portion of input and not the whole input. And using just this portion, each authority needs to generate S and delta asynchronously. This problem is non-trivial even if you assume that each authority looks at the whole input X. Even then, because of the independent nature, there's no guarantee that all the authorities are going to sample the same S and delta. And moreover, we need S and delta to be randomly generated as well. So more specifically about this problem, given a GID, we need S and delta to be same across all authorities. And they also have to look random. Because this is the only random portion of GVW key generation. The rest of it is deterministic. So in order to solve this issue, we can trivially use a PRF. If each authority knows the same PRF key K, then they can use the GID information to sample S and delta. But there's a problem with this approach. Where is K? If each authority has to know the same key K by key generation, then K has to be part of global CRS. But that means even the adversary is going to learn key K and we cannot rely on PRF security anymore and in turn the security that S and delta provide. So in order to solve this, we use non-interactive key exchange. So using non-interactive key exchange, each authority is going to sample a key K using their own secret value and public value from all the other authorities, and then proceed to use the key as a PRF key to sample S and delta. By Nike security, the adversary will have no idea about what key K is, and we can readily rely on pair of security and the security that S and delta. So by using 2 or 3 party Nike that is given by polynomially hard Diffie-Hellman assumptions, we can readily instantiate GVW compiler and construct the 2 or 3 authority QGID MAFE scheme. And in our work, we also show how to bootstrap this to construct any constant authority MAFE scheme from the same polynomially hard Diffie-Hellman assumptions. And we also show how to construct MAFE with arbitrary authorities using sub-exponential public key encryption and random oracles. One open question of our work is corrupting authorities. If you remember, I was saying like each authority is only going to give you one partial secret key per GID. Yeah, that goes out the window when we corrupt authorities. And Brakersky et al. Shows some tighter implications in case of corruptible authorities. And we do have some preliminary results in this domain where we overcome these implications and construct corruptible MAFE from standard assumptions. Thank you.
So when you generalized the Gabo-Cetus construction,
yeah.
You call it one GID, but GID was not part of the construction?
Yeah, because like each authority, the adversary is only going to corrupt one partial secret key, we kind of ignore it from the syntax. You can always include it in the syntax, but GID does nothing in the scheme. Because you can always assume that the adversary is going to corrupt for the same GID, not really.
Great.